Before Kronos builds a machine, we build it 1,000 times in software. A fusion reactor is one of the most tightly coupled physical systems humans have ever tried to engineer. And the only honest way to design one is to simulate it at scale from first principles on some of the largest computers we can reach. Start with the stack. No single code captures a fusion device, so we run a suite. Magnetohydrodynamics for the plasma's large-scale stability, transport for how heat and particles move, gyrokinetics for the fine-grained turbulence, and neutronics for how fusion neutrons deposit their energy in the walls and breeding blanket. 4 physics domains, each a discipline of its own. The hardest of those is turbulence, and it is where the physics really lives. Gyrokinetic simulation follows the plasma at the level of individual particle orbits spiraling along field lines. It is first principles, no fudge factors, and it tells us how heat leaks out of the core, which sets how well the machine confines its plasma. It is also brutally expensive to compute, expensive enough that a single laptop is not even in the conversation. These simulations run massively parallel. The problem is carved into millions of pieces and spread across thousands of compute nodes, all working the same instant, exchanging results at every step. The art is keeping all of them busy and in sync. Increasingly, that work rides on GPUs. The same hardware that trains modern AI turns out to be ideal for the dense, repetitive math of plasma physics. A well-written kernel on a modern GPU does in hours what used to take a cluster days. That is the workhorse of the modern fusion simulation. But the real challenge isn't any one physics, it's coupling them. The plasma heats the wall erodes and feeds impurities back into the plasma. Neutrons transmute the materials change how heat flows. These effects talk to each other continuously. Multi-physics coupling means solving them together as one system instead of pretending they're independent. And they unfold across scales that span an almost absurd range. Turbulence churns in millionths of a second. Material damage accumulates over years. The plasma edge is measured in millimeters, the device in meters. Multi-scale methods are how we bridge those gaps, capturing the fast, small physics where it matters and passing it up to the slow, large behavior of the whole machine. Underneath all of it is numerical machinery most people never see. We break the reactor into a mesh, millions of little cells, finite elements in finite volumes, so the equations can be solved piece by piece. And at the heart of every step sit the solvers, sparse linear algebra, run at enormous scale, doing the actual arithmetic that turns physics into numbers. Running one simulation is a task. Running thousands reliably is an operation. Workflow orchestration ties it together, scheduling jobs, moving data, chaining one code's output into the next code's input. So a design study becomes a repeatable pipeline instead of a heroic one-off. That discipline is what makes the results trustworthy. And here is where it all pays off. Those heavy, offline, high-performance simulations are not just for design reports. They train and calibrate the real-time digital twin, the fast model that runs live alongside the machine. The supercomputer does the deep thinking ahead of time. The twin carries that knowledge into the control room and acts in milliseconds. That is the HPC to twin bridge. One honest note on status. Everything here is validated in open simulation today, benchmarked against known results, and the ultimate test is real data at our first gate. Simulation does not replace the machine, but it lets us find the failures, tune the design, and understand the physics before we ever cut metal. In fusion, that is the difference between guessing and engineering.